All right. So when we did the Lewis formula, sigma bonds and pi bonds only apply to covalent bonding. So if a little while ago we looked over Lewis formulas for ionic bonding and covalent bonding, but if you're asking about sigma bonds and pi bonds, that only applies to covalent bonding. Okay? So a sigma bond by definition, so sigma, and we use that symbol that looks like this. Sigma bonds by definition are those bonds that lie directly on a line between the nuclei of two atoms. Okay? Now all single bonds will be sigma bonds. All single bonds will be sigma bonds. Okay? Double bonds contain one sigma and one pi bond. And triple bonds contain one sigma and two pi, symbol pi, bonds. Okay? So a moment ago we looked at covalent bonding in terms of just using Lewis formulas. And we came up with this Lewis formula. We didn't label it then, but this is a Lewis formula for oxygen dichloride. Okay? So starting with the Lewis dot formula, we could write a three-dimensional structure for this, where we have oxygen with 4 sets of electrons around the central atom. And we call this the electron pair shape. And it's a tetrahedral because there are 4 arms around that central atom here. Okay? This is a tetrahedral electron pair shape. Okay? The next step then when we're doing three-dimensional structures was to take and put or replace shared pairs with this element symbols. So we left the lone pairs alone, just replaced the shared pairs. When we did that, you were supposed to redraw exactly the same drawing, erase, in this case, 2 electron pairs and put on their chlorines. I'm just going to go ahead and put them on there for right now, since this is more review than it is primary instruction. And we end up with the 2 lone pairs over here, and that gives us our, this is still a tetrahedral because there are 4 arms equally spaced around the central atom, but this is a modified electron pair shape. Okay? This bond right here, these 2 shared electrons that are lying on this line are directly on a line between the 2 nuclei of 2 atoms. This is therefore a sigma bond.
You repeat that and I got that right.
What part? This part, what you said?
Yeah.
Okay. This bond right here lies directly on a line. Remember, there are 2 electrons in that we replaced here with this line showing the direction. But this bond right here between this oxygen and this chlorine lies directly on a line between the nuclei of 2 atoms. Okay? Now, this drawing and the molecular shape that follows that, where we erase the electron pairs, this is a bent molecular shape. Okay, this doesn't show single or double bonds or triple bonds for that matter. It only shows the direction. To understand the shape of those pi and sigma bonds, we have to go back to the balloon models we did and the drawings we made from those. Okay, so if I were going to show this using a balloon model, I would have the oxygen right here in the center that we kind of don't show. And we would have a single balloon that would represent that single sigma bond going out there to where the chlorine is. So there's a chlorine sitting up here. So this is what the shape of that sigma bond looks like, or very close to it anyway. And then we have a single balloon going over here to this other chlorine.
Can you leave that part off from the test?
No. All right. And then the two lone pairs are like the round balloons out here. Okay. Okay. So this would be the shape of the orbitals and the bonds that result from sharing two orbitals. Remember, a bond, or a covalent bond anyway, you share two electrons and you also are sharing the orbitals those electrons are in. And when you share two orbitals, one from the chlorine and one from this oxygen, then you get a bond shape. Okay, sort of a wiener shape. Okay, everybody got that? So these are sigma bonds because they're directly on a line between two nuclei. Yes?
For number 69.
Wait a minute, I haven't finished this stuff here. Let's not go to another question yet, unless it's about sigma and pi bonds. Okay, what's the question?
67. What kind of orbitals do sigma bonds come from?
Okay, yes, sigma bonds and lone pairs always come from hybridized orbitals. Sigma bonds and lone pairs always come from hybridized orbitals. So I'm looking here at the oxygen in the center. If the number of sigma bonds plus lone pairs equals 4, if the number of sigma bonds plus lone pairs equals 4, this has to be an sp3 hybridization, because that means I have 4 hybridized orbitals and only sp3 has 4 hybridized orbitals. So this is an sp3 hybridization, okay, on that oxygen. All right. Okay, now that's one kind of sigma bond, or at least that is the way sigma bonds work. What I want to go now to is talking about double bonds for a minute, so you can see where the pi bonds are located. Okay, so I'm going to use a different substance here for the pi bonds. Let's see, we did a Lewis formula and a molecular shape for formaldehyde yesterday. So let's look at formaldehyde again, but look at the shape of the bonds themselves. So yesterday when we did formaldehyde, we found that there was, let's see, our three-dimensional, we had a Lewis formula when we got that, where we had a hydrogen and a hydrogen here and a double bond to this oxygen with 2 lone pairs on the oxygen. That was our Lewis formula when we did formaldehyde yesterday. When we got to the molecular shape, we would have had a trigonal planar shape. We had an oxygen on one of the arms and 2 hydrogens on the other 2. So that's a trigonal planar molecular shape. I'm skipping over some steps because we went through this yesterday. Okay? What I want to talk about, though, is this double bond. This double bond doesn't actually look like this or this. Three-dimensionally, a double bond, what I want to do is take this shape and turn it, flip it. I want, instead of having it sit like this, I'm going to flip it like this a little bit. Okay? And so I'll put the carbon here, and there's 2 bonds between this carbon and the oxygen. And the bond that goes between the 2 nuclei is this cigar shape or the wiener shape, and that's the sigma bond. between the carbon and the oxygen. Okay? Then the second bond has to be the pi bond. And the pi bond runs parallel to this, but it has two parts on the top and the bottom. So pi bond has two parts, like a p orbital has two parts. So pi bond goes across the top and across the bottom. So these two parts here are part of the same pi bond. It's not two separate pi bonds, it's the same pi bond. We could call that pi y, I guess, okay? So those two parts right here are part of the same pi bond. All right? And this sigma bond is just it's a wiener stuck on a stick, sort of, in between the two nuclei. All right? Well, this means that, remember I took this shape here and from being like this, I turned it up on its end. So that means the two hydrogens are going to be kind of in the front and the back. But those are single bonds, and single bonds are always sigma bonds. So the bond going to the hydrogen is a sigma bond. And the bond going to the other hydrogen is a sigma bond. Okay? And then you got the two lone pairs. And the two lone pairs are, remember, always hybridized orbitals, like the single balloon shapes we drew. So those are also hybridized orbitals. Okay? So sigma bonds always come from hybridized orbitals. This bond had to come from a hybridized orbital from the hydrogen and the carbon and the hydrogen. This bond had to come from the overlapping or sharing of hybridized orbitals from hydrogen and carbon. Lone pairs are always hybridized orbitals. So this lone pair is a hybridized orbital, this lone pair is a hybridized orbital. And this sigma bond comes from hybridized orbitals that are shared between carbon and oxygen. The pi bond, on the other hand, comes from unhybridized p orbitals. So pi bonds come from the sharing of unhybridized, not hybridized, p orbitals. On both atoms in the bond. Okay? Yes?
How do you know not to put hydrogen like carbon and then the sigma line and then hydrogen? How do you know which one to put where?
I'm not sure I understand the question. How do I know which one to put what?
The carbon, if you take the carbon and oxygen and the sigma line and then how do you know not to put hydrogen and then the sigma line and then hydrogen? instead of
Carbon, sigma bond, hydrogen here. How do I know to do that?
No, carbon and oxygen right there.
How do I know to put a sigma bond in there?
How do you know which element to use?
Okay. This double bond right here that we got from when we shared electrons yesterday. We did the sharing arrangement, Lewis dot formula. This is the Lewis formula. Okay? If we've got a double bond has to be 1 sigma and 1 pi.
So it has to be the longest two in between.
Yes, that double bond has this sigma bond, and both of these together make up a pi bond. Okay? So there's one bond here, and the second bond is both of these. Okay? These are not two separate bonds. These two parts right here I'm pointing at right now are the same bond. That's just one bond with two parts. Just like p orbitals have two parts, a pi bond has two parts.